Okay, welcome everyone to the seminar. So it's my pleasure to introduce Leonardo Badurina, who's from King's College London. So Leonardo is the PhD student of Chris McCabe and Diego Blas at King's. Well, Diego is no longer at King's, but Chris is at King's. Leonardo's been involved in this quite exciting project in the UK called AION, the AION, which is an atom interferometry experiment which can do a range of things from dark matter to gravitational waves. So Leonardo's a PhD student currently. I think you're presumably approaching the end of your PhD, so I guess perhaps you're on the job market. Leonardo's very good, and I'm sure he's going to give an excellent presentation about this quite exciting new style of experiment. So thanks for waking up to be with us, Leonardo, and I'll give you the floor.
Oh, thank you very much. Thank you, Kieran, for the very generous words in your introductory remarks. So indeed, I'm a PhD student at King's College and London, that is. And so since the very start of my PhD, I've been very much involved in this field of understanding the phenomenology of dark matter searches with large-scale quantum sensors, specifically atom interferometers. So a lot of the things I'll be saying today are based on work that I've conducted with my advisors, Chris McCabe and Diego Blas, but also with other collaborators. For example, Ankit Beneval, who's a postdoc in the group, Jeremiah Mitchell, who's a postdoc in Cambridge, and Valerie Gibson, who's also a leading member of the AION collaboration and who's based at the University of Cambridge. And finally, Peter Wolf and Aurélien Hess from CERTE in Paris. So given the subject that I'll be presenting today, and since I am aware that not everyone is familiar with the concept of atom interferometry or how atom interferometry works in general, I've decided to structure this talk in basically two sections. In the first section, I'll go over the basics of atom interferometry, and I'll try to answer the question of how atom interferometers can be employed in general to perform measurements, that is precision measurements, not necessarily for dark matter related reasons, but just to look for, say, accelerations imparted on atoms or whatever. And then I'll move on in the second part of the talk to explain how atom interferometers can be used to look for dark matter induced effects. And ultimately, I'll show you how future atom interferometers, such as the AION experiment, in at least one of its future iterations, will be able to probe regions of dark matter model space that have been not yet probed by other experiments. So without further ado, let me start off with giving you a crash course in atom interferometry. Now, I put an asterisk at the end of this statement because I am a dark matter phenomenologist. I do not come from the cold atom community. So I'll tell you my understanding of atom interferometry and at least the very basic notions that one needs for this talk. And in general, I believe in working in this field the way I do. So how would I, as a theorist, describe atom interferometry? Well, atom interferometry can be succinctly described as an experiment that measures the phase shift accumulated by spatially separated quantum superpositions of atomic wave packets. Now, this may sound a bit abstract, but I'll try in this first part of the talk to build up on this definition to ultimately give you a pictorial understanding of this experimental technique. But from this description here, we can start off with identifying some key features of atom interferometers. And these are as follows. So firstly, one needs to start off with a quantum system, which is, for all intents and purposes, a two-level system, meaning that we can prepare some system in an excited versus a ground state. And importantly, we want to make sure that the atoms can stay in the excited or ground state for a sufficiently long period of time without too many losses. Secondly, in order to achieve this two-level system, and in order to facilitate the transition from one state to the next, and in order also to manipulate these atomic wave packets as they travel in space and time, this is done using a very special type of laser sequence which will be of key importance to achieve the interferometry. And finally, at the very end of the experiment, there should be some way of measuring the phase shift accumulated by these spatially separated wave packets. And this is done by effectively redirecting the delocalized, if you will, wave packets to a well-defined region of space and time to then perform the so-called phase readout. But again, this may sound somewhat abstract, even maybe unsatisfactory on a theoretical level. So let me try to give you some more of an intuition as to how this technique actually is implemented. So I think that the interesting thing to try to understand initially is how to create these quantum superpositions using atom-light interactions. So in order to manipulate atoms with light pulses, we must recall some important concept that applies in quantum mechanical two-level systems, and that is that when you have a two-level system that is coupled to some driving force, so in our interest we can think of the atom coupled to say the electric field from a laser beam, then this two-level system will undergo Rabi oscillations. What these Rabi oscillations are simply oscillating transition probabilities from going from one state, say the ground state here shown in blue, so GP with some momentum, to some excited state E with some new linear momentum P plus K, where K here is the, if you will, the wave vector of the laser. So it would be the energy imparted onto the atoms by the lasers themselves, by the laser itself. So we can see here in this plot, the transition probability. So if we say you start at time 0 with the probability 1 of being in the excited state, then if I allow my state to interact for a sufficiently long period of time, meaning for a time pi/2 times this, I can't see it here, but there should be a, let's put this here. So pi/2 times 1 over the Rabi frequency, then this will effectively allow the transition probability of going from the excited state to the ground state to be about 50%, and similarly from going to the ground state to the excited state. And so we call this so a pulse that lasts for a time pi/2 times the inverse Rabi frequency, a so-called beam splitter pulse, because for all intents and purposes, it splits, if you will, the ground state wave function into excited and ground, and vice versa, the excited state into ground and excited states. So in the case of single photon transitions, meaning if we had one photon driving the transition from one state to the next, then we can pictorially understand what's going on with these diagrams. So if we have the ground state here with linear momentum P, if I have this green dotted arrow here, which represents a photon, then this will lead to this superposition of states, an excited and ground state. And similarly, we can understand the same phenomenon, but when we start off with an excited state. But what if instead the interaction between the electric field from the laser beam and the atom's degrees of freedom lasts for a time pi times this inverse Rabi frequency? Then in that case, if we look at these curves, we see that if we started off in the excited state, then we have perfect conversion from the excited state to the ground state. And importantly, if we look also at the linear momentum of these states, you'll see that if I started off with an atom with linear momentum P plus K, I'll now have an atom with a linear momentum P. So effectively what this means is that we've been able to reverse the internal degrees of freedom of the atom by changing the ground state to the excited state or vice versa. But we've also been able to effectively add additional momentum to the ground state, or to subtract momentum from the excited state. And so these, in the case of single photon transitions, can be understood again with these diagrams here. So having laid out what I think are sort of the important concepts concerning atom-light interactions, let me give you a pictorial, perhaps, description of how a Mach-Zehnder type atom interferometer would work. And so here, again, I'm anticipating why this is a pictorial a description, because I will be showing to you a space-time diagram for this very sequence. So we can think of the y-axis here, if you will, like space, and the x-axis as time. So we start off with an atom in the ground state, which it has quantum description given by this ground state with some linear momentum p. Then at a time zero, if you will, as soon as I apply the first beam splitter pulse, I consider this the time at which I start recording time. So at time zero, then I apply this beam splitter pulse, which, if you recall, would be the pi/2 pulse defined in the previous slides. And in so doing, I create this quantum superposition of a ground state with external momentum p and an excited state with momentum p plus k. And I've already causing some sort of relative phase shift encoded by this delta phi term. Okay, so after this, the application of this beam splitter pulse, I created this quantum superposition. So I let the system, so my quantum system, to evolve in time. And then what happens is that at a time t, which we call the interrogation time, another important concept, one applies a mirror pulse. And this mirror pulse, if you recall, inverts the internal state of the atom. So if you look at this notation here, the excited state is shown with these red dashed lines, and the ground state with these blue solid lines. So we see that the excited state now goes to the ground state, and the ground state to the excited state. And if you look at the slope of these curves, they should tell you the magnitude of the linear momentum of the center of mass of the wave packet. And so you can see here that the excited state at this mirror pulse will lose also a fraction k of its linear momentum, whereas the ground state will gain a fraction k of its linear momentum. And so this is why the lines are redirected, if you will. So these trajectories are now converged towards a particular point. And indeed, at a time 2t, a final so-called beam splitter pulse is applied. This beam splitter pulse is another pi/2 pulse, which interacts with both arms of the interferometer. And in so doing, one splits the upper trajectory here, which is in the ground state, into ground and excited state, and the excited state in the lower path into excited and ground state. And then what this final beam splitter does, and why it is fundamental to apply this pulse in the end, is that it mixes the relative phase accumulated up until this point by the two states. And because of this amplitude in front of each wave packet, we're able to measure at each detector here, which would be, these would be effectively ground versus excited state detectors, some probability. And so if we imagine, for example, performing this measurement with a bunch of cold atoms, so say 10 to the 6 atoms, then we can think of the probabilities as measured by these detectors as the number of atoms that are measured by each detector. And so what I show here is an actual picture from a paper by Jason Hogan. I forgot to add the reference here, but it's a paper by 2019. And these blobs here are really the images of the atoms at the end of the sequence. So you see that in assuming that the experiment they were done here, that was done here, follows what I'm showing in this very simple Mach-Zehnder situation, then we can see that there are more atoms given by the intensity of the blob here in the excited state than there are in the ground state. So that means that if we look at the now probabilities here, that PE will be greater than PG. So delta phi will therefore be non-zero, or specific, yeah, will be non-zero. And so this is what I would call a theorist's picture of an atom interferometer. And so this is what I think would be sufficient and is necessary really to understand the essence of my work. So without really needing to go into too much of the experimental details, as long as you recall that you can recast the experiment in terms of a space-time diagram, and you understand the key features of the experiment, meaning that you need to create this quantum superposition with a beam splitter pulse, and then you need to effectively share the accumulated phase between the two states with a final beam splitter pulse in order to measure these probabilities, then we're in business. Right, so having said this, however, it is quite unsatisfactory because I haven't told you anything about how to compute these phase shifts delta phi. So what are these phase shifts, and what effects lead to a change in delta phi, which would therefore be a measurable effect? So there are a number of effects which lead to a non-vanishing phase shift. And in the Stanford group, so Dimopoulos, Jason Hogan, Peter Graham, etc., so they presented a very neat way of splitting up the calculation into three distinct parts to basically be able to when trying to understand which effects change delta phi, to sort of have a way of categorizing the effects in a systematic way. And so these three parts are the so-called propagation phase, the laser phase, and the separation phase. So the propagation phase can be simply understood as the phase shift that is accumulated by each wave packet along each path. So that means that if we go back to our diagram here, the propagation phase will take into account the evolution of, say, this dashed red line from time 0 to time t in the upper path, and in the case of the ground state here from time 0 and t in the lower path. And so here this would be the expression that we have. So here we see a sum over upper and lower paths or path segments in a given state. The integral here is between atom-light interactions. So if we go back to this diagram here, these squares and circles would show where atom-light interactions happen. And importantly, the phase itself is proportional to the Lagrangian describing the evolution of the atom center of mass. Now, there are some caveats as to when this applies. So usually this is, you can think of the propagation phase as being described in this way, only if either your Lagrangian is at most quadratic, or when even if it isn't quadratic, the size of the wave function that you're looking to evolve is smaller than the size over which your potential changes appreciably. And finally, what I showed in orange here is the energy of the atomic state. So in a sense, the propagation phase, and this is one of the key take-home messages, will depend in the non-relativistic calculation on the evolution of the external degrees of freedom of the atom, meaning the center of mass of the atom. So this can be some classical, semi-classical type situation, but also on the internal degrees of freedom. So on the energy of the atomic state, or the of the atom in that particular two-level system. So having said what the propagation phase is, let me say a few words about the laser phase. So the laser phase arises as a result of the fact that the laser beam will have some phase which it imprints onto the atom at each atom light interaction points. And you can derive this, this is done very nicely in the Dimopoulos paper from 2009, what the rules are, the laser phase rules. So basically, if you have an atom in a state P, let's say this is a ground state, then if it gains momentum k from the laser beam, then it will gain a phase phi L, where phi L is given by this expression. And if instead it loses energy, it loses linear momentum, then it will have a negative phase imprinted onto it. And so just by looking at this phase here, we see that K and omega and phi, these are all properties of the laser. So K is the wave vector, omega is the angular frequency, and phi is the phase. Whereas what I show in the purple boxes, so X, C, and T0, these instead are space-time, the space-time coordinates at which the atom-light interaction takes place. And so what this means is that the actual laser phase, the total laser phase at the end of the sequence, will simply be a sum over interaction points in the upper or lower paths, where the plus and minuses depend on the transition rules I showed earlier. And finally, the separation phase, which is the last of the three independent parts that add up to the total phase shift measured in an interferometer, instead accounts for the, if you will, the degree to which the interferometer loop does not close in spacetime. So if we go back to our diagram here, so I showed this in such a way that it isn't very clear as to what's going on, but in many circumstances, the lower and the upper paths of the interferometer after a time to t will not exactly overlap. And so that mismatch, if you will, so the degree to which the loop does not close is accounted for by this separation phase. Indeed, what I show in blue here, this delta x, is precisely the wave packet separation between the upper and lower paths before the final beam splitter is applied. And this p bar is the average linear momentum of the two wave packets before the application of the final beam splitter. So in a sense, if one were to construct the perfect experiment, one could possibly create the situation in which this wave packet separation is zero, and therefore the separation phase is zero. Right. So so now we know how to understand an atom interferometer. We know some of the basics as to how an atom interferometer can be understood pictorially, and now we also know how the phase shift calculation is done. But something important that I've omitted, which is an important aside, in my opinion, is that usually it is very hard to compute the phase shift from the propagation phase if one does a full calculation. Meaning, if I were to start off with some Lagrangian and I want to solve Euler-Lagrange equations and further trajectories, and then I want to calculate the delta phi propagation and so on and so forth, that can take quite a lot of time. And also it doesn't always give it isn't always apparent what the leading order effects are. So there's a very simple way instead to estimate leading order phase shift effects from small perturbations. And this is the perturbative approach, which was nicely described by Storia and Tanucci in this paper by 94. It's a very nice paper. It's called actually a tutorial in atom interferometry. So if interested, I highly recommend reading it. So basically what this approach is about is to simply perturb the system that one has. So for example, say that we are interested in calculating the effects from our local gravitational field, then to leading order, one could say, okay, I start off with an experiment in Minkowski space, so flat space-time, there's no gravity, and then I perturb my Lagrangian with effects which will be proportional to gravity, so to the gravitational acceleration, so to g. So these could be, for example, encapsulated in this L1. Then what one does is computes the propagation phase, where the only effect that would go beyond what we had calculated before originates by performing the integral over unperturbed trajectories. So as if we did not know about the existence of this L1 correction to the Lagrangian, but we integrate L1. So in so doing, one gets correct results up to order epsilon in this case, so up to first order in the perturbation parameter. So this is a very important aside, and this is basically what most people use in calculating leading order effects from, say, beyond standard model effects in atom interferometers. So, I have the example here actually about how, for example, accelerations can be measured. So if we suppose, for example, that there's a constant acceleration on atoms, then we can perform and calculate what the leading order phase shift is by correcting our Lagrangian with this new potential here to leading order in G and X. And so via the perturbative approach I mentioned earlier, you can calculate that the leading order phase shift goes like KEF times G times T squared, where KF has to do with the momentum imparted onto the atoms at these beam splitter pulses, and T instead is this interrogation time here. So as we can see just from this expression, the larger T and K are, the better, right? Because we want to make this delta phi as large as possible. And if you look even a bit more carefully, you can, well, you might be able to realize that the area of this kite, this rhombus, parallelogram, whatever, it is sort of related precisely to these quantities here. So in a sense, the size of the signal, so the magnitude of the signal, will grow as the size of the enclosed area in the loop here grows. It's frozen. Okay, right. That said, while it would seem sort of straightforward to increase the size of the signal by increasing T, it isn't at all obvious how to increase K. But the people in the cold atoms community have come up with some very interesting techniques, such as large momentum transfer. So large momentum transfer is the application of a series of successive mirror pulses, so these pi pulses, in order to impart more momentum to one arm of the interferometer versus the other one. So this can be understood by this series of diagrams, which I'll show now. So if we start at time 0, the application of the first pi/2 pulse, we see that the atom in the ground state, now shown in cyan, will be split into 2. Then after a time much less than T, than the interrogation time, another pulse interacts with the upper arm of the interferometer only and originates from the very top, thus leading to a further momentum kick in the upwards direction. Again, another laser beam can travel from the bottom of the diagram, and in interacting only with the very top part of the interferometer, it will impart another kick, again in the upwards direction. Anyway, so you can do this many times, and the result of this operation is that there will be a larger separation, if you will, between the arms of the interferometer than you would have expected from a simple Mach-Zehnder type interferometer with only one pulse interacting with the atoms. And so this is precisely how then one can increase K effective, this wave vector here, by taking n, so the number of large momentum transfer, to values greater than 1. Great. So again, we've also been able to have some intuition as to how the signal would scale with parameters, but what about fundamental noise sources? So as I mentioned in the earlier part of the talk, in extracting the phase shift information, we ultimately need to use a lot of atoms in a cloud. And indeed, by doing these so-called fluorescence type imaging techniques, then one can infer the number of atoms in the ground versus excited states, and these quantities can be recast into probabilities, and thus one is able to extract the value of delta phi of interest. Now, since then this cosine here will be proportional to atom number, cosine of delta phi, and therefore delta phi itself will be affected by Poisson statistics. So if one is able to suppress all other backgrounds, then ultimately the fundamental noise floor that one will get to is governed by so-called atom shot noise. And this means that if I had, for example, n atoms in my cloud, then this means that the resolution per cycle, so per time I perform this experiment, will go like 1/√n. So this means that since we want to make the noise as small as possible, the more atoms I have, the better. But unfortunately, that's not the entire story, because the caveat I used, which is if all other noise sources are mitigated or suppressed, is quite a tricky statement to implement, at least. Indeed, the largest noise which affects these types of measurements is laser phase noise. And this has to do effectively with fluctuations in photon numbers in laser beams. But there is a way of circumventing this effect. And this sort of really dominant noise can be mitigated by using an atom gradiometer. So an atom gradiometer consists of two atom interferometers shown here. So we have the top atom interferometer and the bottom atom interferometer, which are simultaneously probed by the same set of laser beams. So the laser beams here are shown as these wavy lines going up and down, starting at various times. So the thing is that the laser phase imprinted onto each interferometer will be to leading order the same. Therefore, the noise imprinted on the atoms in each gradiometer will be about the same. And therefore, if you do a differential measurement, meaning I measured the phase shift here and I subtracted from the phase shift here, then to leading order, you're able to suppress or at least mitigate laser phase noise. So this is a very important concept. In fact, a lot of interferometers, of these vertical interferometers, like what I'm showing here, this is actually a plot from the AION experiment, will be operated in this way. So with this differential type setup, precisely in order to get rid of laser phase noise. So to conclude this first part of my talk, there are a few take-home messages that I think are important, and specifically they're take-home messages for at least for what is about to follow in my talk. So for our purposes, it is sufficient to describe an atom interferometer just in terms of its space-time diagram. So something like what I'm showing here. It will be also sufficient to use the perturbative approach to compute leading order phase shifts arising, say, from new physics, beyond standard model physics. Also, as we said, assuming that you can suppress all other backgrounds, the fundamental noise source that you're dealing with is limited by atom shot noise. So basically, the more atoms you have in the cloud, the better, the smaller the error on phi is. And also, as we've shown before, the larger the area enclosed by the interferometer, so the larger T is and the larger K effective is, the larger the size of the signal. And the final take-home message is that atom gradiometers are extremely useful in suppressing laser phase noise, thus allowing one to reach this fundamental noise source. So are there any questions so far?
Perhaps I can ask. You mentioned the atom gradiometer technique mitigates the laser phase noise at leading order, what causes it to not be a perfect subtraction of the laser phase noise?
Right. So so in the non-relative, okay, it's a very subtle point. So in the non-relativistic calculation, that the statement is that I made is true. When setting up this calculation in the general relativistic way, the contribution from the different terms in the phase shift are reshuffled between the propagation phase, laser phase, etc. So in that case, you would expect assuming that you have, say, a time-independent metric, you would expect the laser phase at emission to be unchanged as the photon travels across space-time. So in that case, it is exactly correct that the laser phase at the interaction points is exactly the same. However, if your background were slightly time-dependent or very time-dependent, actually this statement would not be correct, because there would be some evolution, and that would yeah. So the cancellation would only be true to leading order.
Cool. Yeah, that is quite a subtle effect.
Yes. So maybe I should stress that what I presented so far is the non-relativistic phase shift calculation, which should be sufficient for non-GR related effects to leading order. All right. If there are no further questions, so let me convince you that this technique actually has some application, and that actually people have invested money in it. And so that's what I'll be saying now. So telling you about future atom interferometer experiments. So again, I have a strong bias towards the AION project, as I'm personally invested in it. So the AION project is a UK-wide community of people interested in building an atom interferometer observatory and network to explore both mid-frequency gravitational waves and ultralight dark matter. So as a dark matter phenomenologist, I'm primarily interested in the first part of the description of the AION project, but of course the mid-frequency gravitational wave, the program of the AION experiment, is extremely interesting, and also when the experiment will be built, and especially later stages of the experiment, it will be able to help us in constraining the mid-frequency gap in the gravitational wave spectrum. Right, so focusing instead on the various iterations of the AION experiment, let me try to give you a timeline of how this project will develop. So the first iteration of AION will consist in a 10-meter tower, which will be built. Actually, people are already building parts for it in the stairwell of the Beecroft building at the University of Oxford. So this will be a 10-meter tower, so over roughly 4 floors, located right in the middle of the stairwell, which will feature, as I'm showing in this AION figure, 2 atom sources, so 2 atom interferometers that are referenced by the same lasers. So again, an atom gradiometer type setup. So this experiment is expected to begin doing data taking for physics searches in the late 2020s. Ultimately, in order to do more interesting physics, and specifically also to do mid-frequency gravitational wave searches, it is important to have longer baselines, because I did not show this yet, but the signal scales with the separation between the atom interferometers. So the longer the baseline, so the longer this tube is, the better. So ultimately, in order to be in the right part of the gravitational wave parameter space, then you need to have at least a distance, so a baseline between atom interferometers of order 100 meters. And so AION 100 aims to be precisely that type of experiment, which will realize this 100-meter type atom gradiometer. The location for this experiment is still unknown, possibly Bowlby, in the Bowlby mine in Yorkshire, maybe at CERN in one of the access shaft, possibly in Daresbury where there's this vertical tower. This is still unknown. But it would be better still to build a kilometer-long baseline. This is down the line in the timeline of the AION project, and it is also unclear as to where this could be built. But AION kilometer would be fundamental for exploring a large part of ultralight dark matter parameter space, and also for performing interesting gravitational wave searches. And finally, the dream would be to put this type of experiment in space. So there's a proposal called EDGE, which consists in having two satellites in, I believe it should be the low Earth orbit, each housing an atom interferometer, if you will. Each satellite has an atom source. The atoms fly within each satellite, and then what you see here, this red fiber link, would be the laser. So you have a laser shining from one satellite to the other, and this would allow you to perform a gradiometer measurement. Otherwise, STE-QUEST would also be an atom interferometer type experiment, but in this case, you would have a dual, so-called dual atom interferometer, which can be understood effectively as having two co-located atom interferometers to perform a sort of gradiometer measurement. Again, so in order to make the AION experiment be interesting for physics searches, a number of very aspirational, ambitious parameters have been proposed, but our colleagues, called ATOM experimental colleagues, tell us that these should be feasible in the very near future. So specifically for AION kilometer, the phase noise here shown, like 10 to the minus 5 radians per root hertz, this would imply about using 10 to the 10 atoms in a single shot. This seems very hard at the moment, but this will become more and more feasible with time. Just to hone into AION 10, so as I told you, AION 10 will be located in this stairwell in the Beecroft building at the University of Oxford. Here, this is a picture of some of the people who attended, I think, the second AION meeting. Unfortunately, I was in Italy at the time, so I was on Zoom, so I'm not in this picture. But anyway, here you see the stairwell. So you can imagine the laser coming in from the bottom of the stairwell being directed upwards, and the atoms being located along this stairwell, like so. So I hope I've convinced you that this technique is sound. There is interest in building such experiments, and there is also the potential of reaching the right sensitivities to detect interesting physics, or at least to constrain large parts of parameter space. So that said, I think now I'm in the position to be able to tell you more about ultralight dark matter signals in atom interferometers. Unless there are any questions on AION, but I wouldn't think so. So if not, I'll move on. So I think we all know this this story, so I'll move quite quickly here. So when talking about ultralight dark matter, what I really mean is a dark matter candidate with mass less than about 10 to the minus 2 eV. And because of its high occupation number, this candidate must be bosonic. And specifically, that means that phenomenologically speaking, it is convenient and also correct to describe this, this field in terms of a classical wave. And so when talking about ultralight dark matter, there exists a finite number of candidates that we can think of, and up to spin 1 and spin 1 included, indeed we can think of vectors such as dark photons, pseudoscalars such as the QCD axion or axion-like particles in general, and scalars, so scalar fields which could arise in dilaton-like models or Higgs portal dark matter. Now, irrespective of how these dark matter candidates transform under Lorentz transformations, let me highlight or review what the universal properties are. So since we've said that these fields can be naturally described in terms of classical waves, the waves themselves can be described as oscillating in space and time, and the oscillation is characterized by the mass. For example, if I had a mass of 10 to the minus 14 eV, this would lead to an oscillation frequency of about 2 Hertz. Additionally, because of the properties of the dark matter speed distribution that sort of we've inferred from baryonic matter in our galaxies, then we would expect there to be temporal and spatial coherences which are related to the dark matter average speed. That means specifically that a candidate with mass 10 to the minus 10 eV would have a coherence time of order 7 seconds and a coherence length of thousands of kilometers. So just to recap, in the case of atom interferometers or gradiometers, at most the largest distance you can probe with these experiments on Earth is about 1 kilometer. So in the case of, say, a candidate of 10 to the minus 10 eV, it would always be in the limit where both atom interferometers in the gradiometer are within the same spatial coherence. And finally, the amplitude scales like the square root of the local dark matter density divided by the dark matter mass. That said, let me make a statement about the phenomenology of ultralight dark matter in laboratory experiments, which I think is important for also, and I hope it will try to convince you as to what the motivation for certain types of signals is in atom interferometers. So we know that ultralight dark matter can induce static or time-dependent signals. So static signals can originate, for example, as a result of fifth forces being mediated by this dark matter particle. So these types of searches in general are extremely difficult to perform on Earth because very many non-ultralight dark matter static effects would be present, and these are extremely hard to distinguish from dark matter induced static effects. On the other hand, time-dependent effects, such as, for example, oscillating fifth forces or the oscillation of fundamental constants due to the existence of a dark matter background, would be still very hard to do, but somewhat easier. Because a time-dependent dark matter signal will have some characteristic frequency, it will have a characteristic frequency spread, and it will be modulated as a function, so over days and years, thus allowing for greater signal discrimination. So what I will focus on for atom interferometry is specifically any time-dependent signal. In principle, atom interferometers would be able to look for static effects. Indeed, I've shown you earlier in this talk the calculation of the constant gravitational background. And we've seen that there was an effect linear in G. So in principle, of course, the atom interferometer could detect some, say, constant acceleration acting on atoms, but it would be very hard to extract a dark matter induced type static effect from the tower of non-dark matter static effects. So let me now give you some examples of the type of dark matter candidates that we can look for in atom interferometers. So firstly, a premise, so linear versus quadratic coupling. So in principle, we can think of any arbitrary interaction, but well, arbitrary with an asterisk, provided that we do not violate any principle of locality or any symmetry principle that we want to preserve. But in general, the simplest types of interactions that one can think of would be linear interactions between scalar field and standard model operators, or if you will, quadratic coupling, so phi squared to standard model operators. Here, d phi is a dimensionless coupling strength, and here everything's normalized with respect to the Planck scale. So assuming that we're coupling, so in this case, assuming that we couple to fermionic masses, then in the presence of an external mass, so say, for example, if I were to perform an experiment looking for effects from this portal on Earth, then the external mass could be the mass of the Earth. So that is, if I were to perform the experiment on the surface of the Earth, the correct description of the field would be given by this equation here. So where we have some static contribution, which however has some exponential fall off. So in a sense, this is not too worrisome, because if one is looking for a time-dependent effect, then effectively only the first part of the right-hand side of the equation is what matters. If, however, one takes quadratic couplings, then there is significant screening on the surface of the Earth. And this arises precisely by solving the Euler-Lagrange equations for the system. And so this means that, as opposed to linear interactions in a scalar field and standard model operators, in the case of quadratic couplings, we would expect the effect to be extremely suppressed. And indeed, I will not, therefore, be talking about quadratic couplings here. So one of the first effects that has been proposed, at least in the context of atom interferometry, by Arvanitaki and collaborators in 2018, is the idea of a linearly coupled scalar field here with, say, electrons and photons. This was already sort of discussed in other papers by Statnik and Hess. And the implication of this type of interaction is that because of the oscillatory nature of the dark matter background, we would expect the electron mass and fine structure constant to oscillate as a function of space and time. And what this means is that optical transitions, since they are proportional to the product of the electron mass, or to linear order, really proportional to the mass of the electron and the fine structure constant raised to some power, where this term here, this xi, is some calculable parameter, this would imply that scalar dark matter would induce oscillations in the transition frequencies. So indeed, for optical transitions, if you will, if you turn on dark matter interactions, we see that the energy spacing between levels will become a function of space and time, and will oscillate indeed exactly the same way the scalar field would oscillate, as this effect is proportional to phi. So why do we care? Because if you recall, I showed you earlier that the propagation phase in atom interferometers, in the non-relativistic case, in the non-relativistic case, will depend on the internal degrees of freedom of the atom. And if you recall, I showed you that the propagation phase was precisely proportional with respect to the energy of the atomic state of interest. So this means that if we are thinking about a dark matter-induced signal which lives in the oscillation of transition energies, then this should manifest itself in the propagation phase, and only in the propagation phase, the leading order. And indeed, this is what we've done, and also what Arvanitaki did, but we did some refined calculation which gave us this correction factor, which is important in compact setups. And so ultimately we end up with some expression or the refined signal amplitude of, induced by this type of linear interaction between the scalar, dark matter, and standard model operators, that goes like this. So we see that delta R, which would be the separation between the two interferometers in the gradiometer, if this delta R goes to 0, then you have perfect overlap between the two interferometers. And if you look carefully, then the space-time diagram for each would look exactly the same. So we would expect the differential measurement to cancel out. And this is exactly what we would find here if we set delta R to 0. If there was no dark matter mass, or rather if there was no dark matter candidate, meaning that the coupling strengths were 0, then this signal would go to 0. So everything seems to scale correctly. So interestingly, AION 10, so the first realization of the AION experiment, would be able to constrain a small slither of a scalar dark matter parameter space that is not yet constrained by existing experiments. So here in orange, I show the exclusion limits from the microscope experiment. So you can see that there is still roughly an order of magnitude that can still be probed by even this very first realization of AION, which is, in my opinion, something quite remarkable. Also, if you look at the size of the electron coupling, so here we basically, what this sensitivity curves tells us is that one would be able to probe coupling strengths at about 10 to the minus 15, EV, dark matter mass, about 10 to the minus 3. This would be with respect to 1 over the Planck scale. So this means that we're already beyond the Planck scale, if you will. Right. So in calculating these projected sensitivities, we assumed that the experiment was limited by atom sharpness. But is this always true? The answer is no. And specifically at low frequencies, the experiment would be limited by a type of noise called gravity gradient noise. Excuse me, there is a phone ringing here. I'll just turn it off, so give me 1 second. Sorry. Right, so indeed, low frequency searches would be limited by gravity gradient noise. But what is gravity gradient noise? So very briefly, gravity gradient noise arises as a result of density perturbations, which affect the gravitational field experienced or seen by the atoms as they are in free fall. And as I hope you recall from the first part of the talk, this sort of time-varying gravitational field would affect the propagation phase and thus lead to a phase shift. Now, we've done a very thorough calculation in a paper that is about to appear on the archive. It's a very long and bulky paper, and sort of we've done the very detailed calculations as to how to compute this effect, and the key take-home messages is that this phase shift here depends on this vertical displacement as measured on the surface of the Earth, and there are models for understanding how this behaves. Importantly, this is some sort of colored type noise, so this vertical displacement increases significantly at low frequencies, and this is why this phase here will become larger than the phase you would expect from, say, atom shock noise. And so very briefly, what we've been able to show is that that the gravity gradient noise below about an EV, a hertz, I'm sorry, so about below a couple of factors of 10 to the minus 15 EV, the sensitivity from large scale atom gradiometers like AION 100 would be somewhat affected by GGN. So we can see that the red regions that I've circled as being as showing the degree to which the atom shot noise plus GGN sensitivity curve does less well than the case where we do not include GGN. which is what people had been assuming for a while. But we still see that in the part of parameter space that is of interest for new physics, this effect is not too dramatic. But this instead would be much more severe in the kilometer baseline. In the case of the kilometer baseline, there's an order, well, several orders of magnitude loss in sensitivity between the atom shot noise limited line and the GGN line. And so this is quite problematic for future searches. So what we notice, however, is that since GGN, this type of background, as opposed to atom shot noise, which is independent of where you position the interferometers, it is dependent on the vertical position along the baseline. So in a sense, one can think of rearranging the atom interferometers within the baseline to recover small parts of parameter space. And this is precisely what we did. And we asked the question precisely is, could we benefit from probing different gradiometer length scales? And the answer is yes. And we invented sort of this new type of configuration with our experimental colleagues called the multi-gradiometer configuration. So this consists in having not just two atom interferometers to perform a single radiometer measurement, but we would have many more atom interferometers along this vertical baseline, and we would be able to perform many cross-correlation type gradiometer measurements. And in so doing, some examples of baselines, etc., we would be able to recover some parts of parameter space which had been lost due to this due to GGN. So in a sense, this type of configuration would allow us to suppress GGN specifically between about 0.1 hertz to 1 hertz. And so without doing any more sophisticated type of active noise cancellation, we would be able to recover about an order of magnitude in this part of parameter space. Okay, so I completed my discussion on scalars. Let me say very briefly a few words on vector, ultralight, dark matter. So so far, the main focus of the vector dark matter program at AION, or in general at atom interferometers, has concerned the possibility of having a dark matter candidate, a vector which is minimally coupled and anomaly free, and this is coupled to baryon minus lepton number. This is indeed one of the simplest realization for a minimally coupled vector photon. Now, the implication of this type of interaction is that at low energies, effectively one can think of this Lagrangian, where effectively we have the dark photon in coupling to a neutron current. So what this means is that at low energies, we would expect atomic species with different neutron numbers to experience a different force. Indeed, the Euler-Lagrange equations for the test particle, so an atom with a certain number of neutrons, which would give rise to this B minus L charge, which effectively is just neutron number, this would impart some force on the atom. And indeed, one can think of this, this force as originating because of the existence of some dark photon electric field, which would scale with the square root of the local dark matter density. And because of the small size of the speed, the virial speed of the dark matter, we would expect the equivalent sort of the magnetic field of the dark photon to be vanishingly small. And so to leading order the effect, so this beyond standard model additional force, or fifth force, if you will, acting on the electron would depend exclusively on this electric field from the dark photon. So we've calculated the effect from this this additional acceleration using the perturbative approach that I mentioned at the beginning of the talk. And to leading order, we can see that the effect at small dark matter masses, so for small omega or m equivalently, see that this effect is independent of m. So that means that we would expect the amplitude to be constant at very small masses. And this is exactly what we see in these red lines. So these are the sensitivity curves for certain resolution of accelerations. And we see that as you go to masses below to 10 to the minus 15 EV, then these sensitivity curves flatten out. And instead, there is a loss in sensitivity at higher masses as a result of the fact that this object here, so the sine squared of omega t over 2, this quantity here will get smaller and smaller because the duration of the experiment is such that there is no longer a resonant enhancement of the signal. And finally, some new ideas, actually very new ideas that I've been developing with Diego Blas and collaborators from CERTE, is the possibility of looking for axion-like particles, and specifically axion-like particle ultralight dark matter. So it was recently shown, or at least represented in the literature by Kim and Perez, that if you have, which is quite a general statement, if you have an axion-like particle coupling to the gluons, specifically GG dual, and recall this theta here is a dimensionless term which depends on the axion or ALP field divided by the axion decay constant, then you would expect the mass of pions to well, now be time dependent from the fact that the theta term here would be proportional to the axion field itself. And what was highlighted in this paper, which is also known in chiral perturbation theory, is that the mass of nucleons will depend to one loop on the mass of the pion squared. So since I showed you here that the mass of the pion squared is proportional on theta, which depends on A, this means that the mass of the nucleons, so the neutron and the proton, is expected to oscillate in space and time as well. So this is very interesting because this implies that in the presence of an ALP background, the mass of the pion will be time dependent, which in turn implies that the mass of the nucleon will also be time dependent. And indeed, the effect on nucleons will depend on the variational shift of the pion mass. And what this implies is that atomic masses are also expected to oscillate in time. And therefore, the effect that we would expect is that of something like an effective equivalence principle violating phenomenon, or if you will, a fifth force slice effect acting on atoms. And so, as I mentioned at the start of this talk, since atom interferometers are excellent accelerometers, they're sensitive to accelerations, it should be, I mean, it is quite straightforward to calculate what the leading order effect from such an effect would be. Indeed, this is what I calculated. This is a preliminary plot, so take it with a grain of salt. Depending on the type of experiment that you want to construct, so if you had something like an STE-QUEST type experiment, meaning space-based experiments with two co-located atom interferometers with different atomic species, then provided that the nucleon number difference delta A is not too small, then you would expect the sensitivity curve to be given by this red curve here. If you had something, by this purple curve here. If you had something like edge, so an edge-like experiment, meaning you have two satellites that are very well separated, then you would expect the signal instead to be given by this red curve. And so the very exciting thing is that atom interferometers, it would appear, in however these very sort of more futuristic realizations, would be able to probe interesting regions of ALP parameter space. And interestingly, this part of parameter space would be very hard to probe with Earth-based experiments because of something that was discussed in a paper by Junwoo. I forgot his name. Anyway, some people in 2016 about the possibility of the axion developing a static profile. So basically meaning that Earth-based experiments would have a tough time constraining parameter space in this region here. So to conclude, to summarize what I've been saying. So atom gradiometers, I hope I convince you that they are extremely versatile instruments for performing extremely precise measurements of all sorts. But specifically, at least for what I'm concerned, there will be excellent devices for performing searches of ultralight dark matter. I showed that the first stage of the AION experiment specifically is so well underway and is projected to be able to probe new regions of scalar ultralight dark matter parameter space. But more futuristic, if you will, realizations of AION and AION in space, that is EDGE or STE-QUEST, are projected to be even more powerful probes of scalar, vector, and also axion-like particle ultralight dark matter in regions of model space that have not yet been probed or at least constrained by other experiments. But what I've said so far is certainly not the end of the story. This is just the very tip of the iceberg. There are many, many more signatures to be explored. This is indeed something that I'm working on a daily basis. This is if you're thinking about decoherence effects or phase shifts from more massive type dark matter candidates, say sub-MeV dark matter candidates. Also perhaps looking for the signatures from transient phenomena like axion mini clusters, dark photon stars, etc. So that's all I wanted to say. Thank you very much for your attention and for the invitation. If you have any questions, I'd be very happy to answer them.
All right, thank you very much, Leonardo. Yeah, do we have any questions? So I guess some people may have to go, but maybe we can get a few questions from the audience. Bruce, do you want to go ahead?
So just for clarification, when you were discussing gravity gradient noise, I mean, are we talking about ocean waves and trucks driving around or what?
Right, so specifically I was thinking about Rayleigh waves from potentially, yes, seismic activity. So let me go back to, yeah, so we were assuming Peterson's high and low noise model, which do not, if I recall correctly, make any specific assumption as to what the origin of the perturbation is, of the vertical displacement is.
Yeah, sorry, the frequency, the plot went by a little too quickly for me to see. So we're talking about tenths of a hertz from 10 hertz down to a tenth of a hertz or even very low frequency. So.
Mm-hmm.
And I guess I just didn't have a feel from the presentation what sort of amplitude, I mean,
right,
is required. I mean, what sort of mass moving through what sort of distance is required to make a meaningful perturbation in this case? It would just, could you make it more concrete?
Right, yeah, so a fellow PhD student at King's College has been working on, for example, the phase shifts induced by moving masses, say a lift located close to the gradiometer, and in that case the effect is quite dramatic. So the effect from a moving mass about, if I'm not mistaken, 10 meters away or so from the gradiometer would be at least 2 orders of magnitude greater than the atom shot noise level.
Okay, so this is dealing with the fact that you are building the experiment in a stairwell in Oxford rather than in the middle of a desert.
Exactly. So what I'm showing here, however, would be the, if you will, the best case versus, so this would be the worst case scenario if we take Peterson's model as giving some ideas to what the vertical displacement would be, and assuming that Rayleigh waves would be the dominant source of noise, then we would expect the sensitivity curves to look somewhat like this. So this is just a way for us to have some sort of idea as to what the effect from GGN would
Okay,
be.
so the point is it's relatively massive objects very close by.
Yes.
Not
yes. In principle, though, the motion of very sort of well understood objects, to me, would not be so much of a problem, because if one is able to describe the object quite well, you can also simulate the phase shift you would expect from that moving object, and so subtracting that from the data should be quite straightforward. The problem is, instead, if you have
modeling a lift would be problematic. You've got the lift and you've got the counterweight. You've got different people getting into it at different times, and
yes.
it operates on demand. Yeah, so that would be a pest, I can see.
Yes, yes.
Does anyone else want to go next? In which case I can get. So I was also wondering about the gravity gradient noise. So you have this quite dramatic loss of sensitivity at very low frequencies. I guess, is this because your model, the noise is getting worse and worse and worse as you go to low? But in when you were making your plots showing the different strategies for mitigating it, I think you didn't recover the sensitivity in that low mass region. Is there a fundamental reason why? Yeah, so these sorts of plots.
Yes. So our understanding is that if you will, the decay length of, so I didn't say this. So the phase shift from Rayleigh waves would have this exponential suppression as you go underground. And this exponential suppression is related to the frequency of the wave. So what this means is that at low frequencies, the decay length is extremely long, which means that the GGN contribution to the phase would scale linearly, just like the dark matter signal. So basically, it's very hard to disentangle the two effects, and this is why there is a progressive sort of loss in any advantage in using this multi-gradiometer type setup, where we probe different length scales down the interferometer baseline.
Well, I'll keep going in that case. So do you have you've shown the effect of this for the scalar case. Do you expect the same qualitative impact for like a vector and these axion-like particle projections as well?
Right. So in the case, so if we go back to the vector case, so in order to detect this signal, you need to have a dual species interferometer, which is basically like a co-located atom interferometer. So in that case, since you can think of the masses as being the leading order at the same position, you would expect both masses to see the same GGN gravitational field, and so the difference between those two phase shifts would vanish. Yeah. So that's why there's this much better scaling at low dark matter masses.
Is there some limitation of the dual species atom interferometers that I'm missing? Because it seems almost like that's the way you'd want to go to do that, rather than having this really long experiment which suffers this problematic source of noise. Is there some other issue with doing this dual atom type?
So to look for mid-frequency gravitational waves, you necessarily must have an atom gradiometer type setup like the one that AION will be using. So the idea is to try to do as many possible searches using the same configuration.
Yeah.
But what might happen at some point in the future is that, say, AION kilometer is running and also AION 100 exists, and they're in two different locations. Then I would be very happy to see one, say, work in a dual species type setup and the other one instead working a different type of setup, and then having MAGIS in the US working in maybe in an even different configuration, such that one can do simultaneously with 3 different detectors. a very sort of generalized search.
Yeah, I see. Okay, so you're optimizing for the gravitational wave sensitivity as well as the everything else. Yeah, that's the thing I missed. Yeah. Okay. All right. Since we're a bit over time, I'll stop the recording there.